everyone. I'll get started in just a second. I'm checking my sound first to make sure that everything is good on my end. And I see that there are a few of you that have signed into the chat so far, so thank you so much for showing up. And I'm going to start today by introducing both myself and the language before we dive into the tutorial on JuliaBox. So first off, my name is Jane. Right now I'm working for Julia Computing, and I'm also a grad student at Caltech. So I started learning to program only a couple years ago. Initially, the motivation for that was to do some scripting that would allow me to basically process my data and that sort of thing. And I started originally learning to program in Python. And then it was, I messed up timelines actually, sorry. So it was more like 4 years ago I first started learning to program, and about 2 years ago that I first came to Julia from Python. And I'll talk in this introduction about the language, about why I decided to start making that switch. But first, we'll talk a little bit about why the Julia language has come into existence, why we want yet another language. Then we'll talk about an application of Julia and see what it's like to use Julia in practice before diving into the tutorial on JuliaBox. Also, one other thing I should say is that throughout the tutorial, I'm going to be checking in on questions on chat to sort of catch up and make sure that I've been able to address any of your concerns. Sometimes we'll also get other helpers coming in to address questions. And it looks like my audio could use some upping. So I just increased my audio. Hopefully that helps. And I'll also move the mic a little closer and try to speak up. So ping me again, either on the YouTube chat or on Slack. I'm X or Jane on Slack if you're on the Julia Slack channel, to let me know if you want me to increase volume. For now, back to my slides. So first off, why do we want another language? So the first question that we might ask when we show up for a Julia tutorial is, with all of the existing languages out there, why is Julia being created, and why are hundreds of people contributing to this new language? So what we see on this slide is an image that I found online by a gentleman named Paul Bowler, which is sort of a periodic table of programming languages where different programming languages are color-coded by the characteristics or the features that they have to offer. And so with all these different features, all these different characteristics in different programming languages out there, what does Julia bring to the table that isn't already on the table? So the idea is that even with all the existing languages out there, we still have a problem called the two-language problem. And what is this two-language problem? So the two-language problem comes from this traditional divide between performant and productive programming languages. So traditionally, on the one hand, we have lower level languages like Fortran and C that allow us to generate really efficient machine code that's really highly performant. And on the other hand, traditionally, we have higher level languages that allow us to be more productive as programmers, languages like Python and MATLAB and Ruby that allow us to start writing code more quickly as the programmer. And so the idea is that we have this trade-off between the performance and the productivity of the programming language that we choose as our tool. We have to choose between writing efficient code and writing code efficiently. But the true trade-off that we're faced with here isn't really just a dichotomy, it's really a trichotomy, because we've sort of assumed in talking about this first trade-off between performance and productivity that we were working with a general purpose language. If you want to work with a domain-specific language or special libraries like NumPy, those tools can allow you to write fast code really quickly. But then the scope of the tools that you're using will be limited. So for example, if you're working with Python's NumPy, it's tremendously fast. It's also very easy to use, but then you're working with arrays rather than maybe more complex or more general data structures. And so the idea of the trade-off that we're really faced with is this this trichotomy between performance, productivity, and the generality of the programming language that we choose. And the traditional workaround when we want all three of these things for our workflow is to work with two different programming languages. So the way that this traditionally plays out is that a programmer or a software developer will start by prototyping in a higher level language like Python or MATLAB. And once they have something that's working, once they have sort of a proof of concept, and they get to the point where they need their computations to hit scale, it's at that point that they'll transition to a lower level language, that they'll translate their prototype in Python, for example, to a language like C or Fortran. And so that's where this name, the two-language problem, comes from. And Julia was designed to address this two-language problem, where the tagline of Julia is, looks like Python, feels like Lisp, and runs like C or Fortran, with the idea being that Julia can offer you productivity, generality, and performance. So when we say that Julia offers all three of these things and helps us avoid trade-offs, I'll talk you through what I mean when I refer to each of these characteristics. So we can start by talking about Julia's performance. Now, in the tutorial today, we're going to look at a benchmarking example where we'll look at different implementations of the sum function. So the sum function is going to take some vector and it's going to add together all the elements of that vector. And for the purpose of benchmarking this implementation, or rather this function in various implementations, we're going to use a vector that has 10 million different elements. And when we run our implementation of this sum function in C with our 10 million element vector A, it's going to take order of 10 milliseconds to perform that operation. When we do the same operation using a Python implementation, where both our C and our Python implementations are handwritten, we're going to see that it's going to take order of 500 milliseconds to do the same operation in Python. And then when we move to a handwritten implementation in Julia, we're going to see that the time of execution is going to be back down to order of 10 milliseconds. So we'll see that Julia's speeds are really closing in on C runtimes. So then we can talk about the productivity of a programming language. And one way that we can do this is by comparing the syntax of a language like Julia with a language like Python that's known to be productive and high level. And so we can do that by looking at the bits of code that we actually use to implement the sum function. And so I here have on the left the block of code that we use to implement the sum function in Python, and on the right the code that we use to implement the sum function in Julia. And so what we see is that I've put in bold the differences between these two blocks of code. So we do see some differences in required keywords. So for example, in Python we have the def keyword and the colon, whereas in Julia we have the function and the n keywords. But other than that, we can express ourselves in pretty much the same way in Python and Julia, but we're going to be getting more than an order of magnitude speed up when we use the implementation on the right in Julia. And it was this sort of difference that got me personally really excited about coming to the Julia language and starting to learn a new tool. So as I said earlier, I started as a Python programmer, teaching myself to program through, I don't think I mentioned this earlier, but I used some online tools like a course through edX and a course through Coursera. And I had been using Python for my graduate research, but I was starting to get to a point where I was hitting bottlenecks with some of my work. Some of my calculations needed to run overnight to get run without totally jamming up my machine during the day, without taking the additional level of overhead of transitioning to like a cluster. I had started doing my calculations locally, and I was still doing them locally at the time that I was hitting these bottlenecks. But I had a friend who had gotten really excited about Julia. He was working in a combination of C and MATLAB for his own graduate research, depending on how big the problem he was trying to solve was. And at some point, in his enthusiasm for Julia, he decided to take a piece of code that I had written in Python and translate it to Julia for me. And really, the changes that he had to make to the code that I had written to put it in Julia were really minor. But in spite of how minor the syntactic differences were, the code that he had written was more than an order of magnitude faster than the code that I had written. And so seeing that I could get such a huge performance improvement without really needing to do that much to learn a new language coming from a Python background was what got me really motivated about this opportunity to learn a new language. Okay, and finally, the third thing that I said that Julia offers is generality. So we can talk about generality by comparing Julia to a Lisp, or how working in Julia might feel like working in a Lisp. So Julia is it's a dynamic language. It's homoiconic. It offers metaprogramming facilities, so you can program with macros, for example. And the design paradigm of Julia is multiple dispatch. And we'll also talk about that during the tutorial to give you a feel for what multiple dispatch is and why Julia is fast. Okay, and the fact that Julia is such a general and expressive language is what allows Julia to be mostly written in Julia itself. Now, one of the things that's really cool about the fact that Julia is mostly written in Julia is that this means that the line between users and developers of the language really starts to blur. So, traditionally, high-level languages are written almost entirely in lower-level languages, which means that there's a divide between the people who work in the language and the people who work on the language. But in Julia, a lot of our most important contributors to the language are people who have come in, without, like formal CS training. They've come in just as users of the language who, being users of the language, were able to really open up the hood, look at the source code, and start making tweaks to the base language when it suited their needs, or when that was the thing that seemed the most fun to them at any given time. Okay, so this is why Julia has come into being, to address this two-language problem. And now I'll talk about Julia in practice before diving into the tutorial. But first I'm going to flip back to some questions to see what we might have gotten so far. Okay, great. It sounds like fixing my audio helped. And then other than that, we have some comments and a question about zero, the zero function, that I can answer later if possible. And I think I'm gonna bop over to the Julia Slack. Give me just a moment. And I'm going to see if we can we're getting requests for a moderator on the chat, and so I think I'm going to ask within the Julia community on Slack if we can get somebody to help out with moderating. I was hoping to look at the questions myself, but it might be useful to have another person. And let me send them the link. Okay. All right, great. So hopefully we'll get an extra moderator to help out with the live chat and fielding some of your comments. But for now, let's dive into an application of Julia to see what it's like using Julia in practice. And the example that I always like to talk about is the Celeste project. So the Celeste project took data from the Sloan Digital Sky Survey, which was an effort to collect data on 35% of the visible sky. And over the course of this survey, the Sloan Digital Sky Survey collected about 178 terabytes of data, which, for your reference, I always forget what these different prefixes mean, but tera is 10 to the 14. So we're talking about order of 10 to the 14 bytes, which would require about 25,000 DVDs to store that amount of data. Another silly statistic that I like to include, just to give you a better sense of scale, is that if you wanted to print that amount of data on written paper, it would take you, about 150,000 pickup trucks to lug around that much paper and that much data. And so the idea is that the first, decade and a half that this data set was around, there wasn't a whole lot done with it. But then a team of researchers came together to form the Celeste research team. And what they decided to do was to write code exclusively in Julia that would run on NERSC supercomputers. So NERSC is the supercomputing center up at Lawrence Berkeley National Lab in the Bay Area. And so harnessing both the power of Julia as their software and these NERSC supercomputers as their hardware, they were able to catalog 188 million stars and galaxies. So this meant identifying the colors and the brightnesses and the morphologies and the locations of all of these different astronomical objects. And they were able to run the calculation that generated this huge catalog in under 15 minutes. Now, in performing this calculation, Julia became the third language to join the petaflop club after C and Fortran. So it was the first high-level language to be able to run more than a petaflop per second. And in doing this calculation, Julia made use of over 1 million threads and 9,000 nodes. So this gives us a sense of Julia's ability to distribute on highly parallel machines. So then the next natural question is, what did Julia actually bring to the table for the Celeste research project? Because the project in and of itself is impressive, but what would the project have looked like in the absence of Julia? And the first natural question might be that Julia was designed to address the two-language problem, and so absent the use of Julia on this project, perhaps a language like MATLAB and C would have been used together for the project, and maybe that would have introduced some inefficiency in the workflow of the team, and that they would have had to write out only one draft of their code, but then translate into a lower level language at the end of the day. And while that's true, really the impact of using Julia on this project was more profound than that, because the way that the two-language problem plays out on a team like this is somewhat different than the way that it looks when we're just talking about an individual being faced with the two-language problem. So, the Celeste research team brought together people with various backgrounds. So there were, physical scientists who were the domain experts, there were statisticians, there were computer scientists who were the HPC experts. And the way that the two-language problem plays out on a team with such diverse backgrounds is often that the domain experts will be the ones to write the higher level language implementation. And it's only really when they're done that they'll then pass the baton off to the lower level language experts, who will then do that translation to get more performance out of the code base. But the fact that on the Celeste project, the entire team was working in Julia from the beginning meant that that there was one code base, that the entire team was really able to function as a team, and they were able to iterate more rapidly. So at the end of the day, the science and the implementation of the science were really able to evolve together. Now, outside of Celeste, which was largely an academic project, though there were industrial collaborators involved as well, we've seen Julia uptake across industry. So this is a list or a slide showing some of the logos of some of our users and partners and employers that are taking Julia programmers these days. And beyond that, as of August 2018, these are some of our growth statistics to give you a sense of Julia uptake. So we're at over 2 million downloads now. The Julia 1.0 release was in August, and this is the first tutorial where I'll actually be using 1.0 on Julia Box. Now, after today, if you're interested in continuing to learn the language, I hope that you'll join us on some of our online communities. We have really active communities on Slack and Discourse and GitHub where the language is being developed. Particularly if you have questions about using the language, Slack and Discourse are really where you want to go. And you're also welcome to contact me if you hit any hurdles, where my email is jane@juliacomputing.com. So with that, if you haven't logged in yet, we can get started with the tutorial. So if you haven't logged in yet, go to juliabox.com. And I will show you in a moment what that looks like. So let's see. All right. I'm going to field a couple of them, or at least address some of what has happened on the Slack before I dive into tutorial notebooks. And actually, maybe I will... I'll leave up the slide so you know where to go. juliabox.com. All right, so now I'm going to flip over to a web browser so that I can show you how to log into juliabox.com. Now what we're seeing here, first off, is the julialang.learning page, and I showed that as a resource because I wanted you to be able to see where we have upcoming tutorials. But I'll flip here over to JuliaBox. If I go to juliabox.com, what you'll see when you show up at JuliaBox, oh, and I've already logged in, so it's like I've cheated. I will log out. What you'll see is that you have the option to log in with GitHub, Google, LinkedIn, or regular email. So here I will log in with GitHub. Once you log in with GitHub, you can hit launch, and that will bring up the Jupyter notebooks that you'll be able to run in on the cloud without installing anything. And let's see if I can pull this up. Once you've hit launch, I'm going to be flipping back and forth between two different browsers because I had some things preloaded. Once you've hit launch, a set of directories will come up, including one that says tutorials. So you should be able to click on tutorials. Mine might get angry because I logged out and logged back in. So if I try this, yeah, I get a server error because I cheated. So you have to wait for this launch to happen. If we have a bunch of people coming on at once, we have nodes spinning up to accommodate demand, and so it might take a moment. I think what I'll do in the meantime is that I'll put in the chat what to. Oh no, okay, it's loaded. Great, so I can just show you. Okay, so once you've hit launch, you'll see this tutorials directory. If you hit tutorials, inside tutorials, you'll see a subdirectory called introductory tutorials. Now, once you're inside introductory tutorials, the tutorial you want is this one called Intro to Julia. That's where all the materials I'll be using today are. And then inside Intro to Julia, we have notebooks numbered from 0 to 12, and that's what we'll be covering today. If we have time, and depending on how I'm feeling, how things are going with chat, I might take a brief break. Maybe like 5 minutes or so in the middle. Otherwise, I think I'll cover a notebook and then I'll flip over to chat to, actually that doesn't quite make sense. So there's a slight lag between my speaking and your hearing me to prevent buffering and make sure that data gets transmitted nicely. And so I think what I'll do is I'll cover 2 notebooks, and then, yeah. Or I'll work in a little bit of a lag with answering questions, but I'll try to answer your questions at the end of every notebook. I'll cycle back to the chat to see what I might need to clarify at that point, because I'm sure I'll be saying things that aren't adequately clear for everybody. So we want to make sure that the tutorial is accessible. So with that, I'm actually going to be working on a local copy of these notebooks. So I just flipped over to my local copy, and let's get started with this notebook 00 on Jupyter Notebooks. So the purpose of this notebook is to show you what it's like to run within a Jupyter notebook in case you're not familiar with this environment. Now within a Jupyter notebook, we have some cells, so these blocks that I've selected here. Some cells have been designated as markdown cells where we can provide instructions, and others are code cells. Now code cells are a slightly different color of gray. They have this outline around them, and we also see to the left of the code cell that there is an indicator that says in for input. So if we select a code cell and then we run it, and we can run a cell by either, we can select and hit Shift and Enter. We can go to cell and, for example, hit run all if we want to run all the cells in a notebook. Or when a cell is selected, we can hit the run arrow right here that I'm highlighting. So however we want to run a cell is just fine. And once you run a cell, you'll see that the last line in the cell that you've run will print to standard out. So here we're seeing that 4 gets printed out, but not 2. If you want to suppress the output for the last line of a Jupyter cell, then you can put a semicolon after that last line, and then it looks like nothing happened. Now, both within a Jupyter notebook like this and in a Julia REPL, or read eval print loop, we can enter the help mode by putting a question mark at the beginning of our prompt. And so if I say question mark println, what I'm doing is asking for help with regard to the println function. So if I run this, we see that we're going to pull up documentation for the println function, which is the most common way to print in Julia. And this will work for any Julia function and generally any Julia object that includes documentation, including documentation that you've written yourself. Now, besides entering help mode, we can also enter shell mode by putting a semicolon before Unix or generally *nix commands. So if I say semicolon ls, we can see all of the files that I have in my current directory. And if I say semicolon pwd, we can see what my current working directory is. Now, beyond this, some other things that we might want to know about Jupyter Notebook so that you can play around in this environment while we're doing the tutorial is that you can add new cells with this plus operator shown here, and you can delete them with these arrows, or not arrows, scissors right here. Similarly, if I were to select a cell and go to insert, I could insert cells above or below in that way. And because there is a bit of a lag, what I'll do is I'll cover notebook 1 and then I'll flip back and answer questions about this notebook 00, or at least I'll check to see if there are questions so far. So now I'm going to dive into notebook 1. Notebooks 1 through 6 are really our whirlwind tour of Julia syntax, to give you a sense of how similar working with Julia might be to working in another high-level language like MATLAB or Python, for example. And so this notebook 1 on getting started is where we'll see how to print in Julia, how to assign variables, how to comment, and what the syntax in Julia is for basic math. So first off, we often use this println function to print in Julia. And so when I do that, we're going to see that this string, I'm excited to learn Julia, gets printed to standard out. And then to assign variables in Julia, we don't need to say what the type of a variable is up front. We can just say, for example, my answer equals 42, and now I've created this variable called my answer, which Julia can tell is an int64. And we can see that by using this type of function called on the variable to see what the type of that variable is. We see here I'm creating this variable called mypi, which Julia can tell is a float 64. And in this third example of creating a variable here, I'm assigning the string smiley cat to the smiley cat emoji. And we can see here that smiley cat emoji is a string. Now, programming with emojis in Julia is a great example of a way in which Julia is generic. And I'll talk a little bit about more of that in a second. But for now, and one last thing to say about assigning variables in Julia is that if I were to reassign a variable of a given type to another value of a different type, there's no issue there. So for example, if we reassign smiley cat emoji to now equal a 1, and then ask for the type of smiley cat emoji, we can see that it's now an int64 rather than a string. And now back to this idea of genericity in Julia and being able to code in emojis. For example, the fact that we can use emojis in coding means that we can, for example, assign smiley face to a 0 and frowning face to a -1, and now we can create Boolean statements like the one that I show here, where we see that we've now taught Julia that smiley cat emoji plus frowning face equals a happy face. And that is a true statement now in our code. Okay, so how to comment in Julia? We can comment in Julia by using a hashtag or a # to generate a single line comment. So if I run this cell, nothing has really been executed. And we can generate multi-line comments by enclosing our multi-line comments inside a double, or rather a pair of # and a pair of equal signs. Now the syntax for basic math will probably look pretty familiar to most of you, with the difference, or the main difference that I'm able to identify being that if we want to exponentiate something in Julia, we use the caret sign. So we say 10 caret 2 to get 10 squared rather than using the double star as is done in Python, for example. Otherwise, we have the plus sign for addition, the minus sign for subtraction, multiplication. Here we have division, and then this is the modulo operator that gives us the remainder when we divide by the number to the right of the percentage sign. All right, so that's it for notebook 1. Let me flip back to chat and see how we're doing. Okay. All right. Okay. Happy to see there's some discussion going on in the chat. I'm always happy when that's active. Otherwise, it looks like there aren't any questions so far about notebooks 0 or 1. So I'm going to flip back to notebook 2. Okay. So notebook 2 now is on strings. So in this notebook, we're going to see how to create a string in Julia and then how to interpolate and concatenate strings. And if those are unfamiliar terms, then don't worry, I'll explain them in a moment. But first off, how to create a string. So if we want to create a string, we need to enclose our characters in either a pair of double quotation marks or 3 pairs of these double quotation marks. So the first way that I might create a string is using a single set of double quotation marks. So here I'm creating a string called S1. And the second way that we might do this is by using this triple set of double quotation marks. Now, one of the differences in this second type of string that I'm creating is that it picks up on some additional formatting that we might add to a string. So for example, here I've added a bunch of return statements or new line characters to this string called S2. And if I run this, we see that Julia added those new line characters to the end of my string. Additionally, it's unambiguous in the second case of creating a string what it means to quote inside of a string. So here in the string, look mom, no errors, I can put errors in double quotation marks and everything is fine. If I try to put error inside double quotation marks in the first type of string, we get an error, and the reason is that, or one of the reasons, this is actually not the error message I'm used to seeing here, but the reason that we might get an error here is that it's ambiguous as to where the string actually ends. So those are 2 ways to validly create strings. In other languages like Python, it's possible to create strings by enclosing many characters, many characters inside of a single set of quotation marks. And that does not work in Julia because a pair of single quotation marks in Julia denotes characters. So here, if I put the letter A inside these single quotation marks and then say what is the type of this single quoted A, we see that it's a char, which is the Julia concrete type for character. Okay, so string interpolation is the next section. String interpolation is when we want to add a value or an expression inside of a string, rather than just having the name of the variable that we want to add being read as text, for example. And I'll show you what I mean now in a second. So first we're creating some variables here called name, num fingers, and num toes. And then let's say that I want to throw the string Jane inside a string, or the integer 10 inside a string, using these variables that I've created. To do that, I would just throw a $sign next to the names of those variables inside my string. So here if I say, hello, my name is $name, we're seeing that the string Jane gets interpolated. Furthermore, you can interpolate not only individual variables, but expressions that contain variables. So here, what I've done is that I've put an expression that I want to evaluate inside parentheses, where I'm adding num fingers and num toes together, and then I've put a $sign now outside to the left of these parentheses. So here we see that the numbers 10 and 10 get added together to generate the number 20 before 20 is thrown inside of the string that's being printed out here. And lastly, in this notebook, we'll talk about string concatenation, which is a way to join multiple strings together to create longer strings. So here, we're creating a string called S3, another string called S4, and then we're bringing back smiley cat emoji, now with the number 10 assigned to it. And the first way that we might concatenate the strings S3 and S4 together is with the string function. So if I pass these strings S3 and S4 as arguments to string, we concatenate them, we get a single output string. Now the string function will take arbitrary input arguments and arbitrary numbers of input arguments. So we can pass, for example, an integer, like smiley cat emoji, to the function string. And also we can pass, for example, 3 or 4 input arguments to string rather than just 2, as was done here. So in this case, we get the response to how many cats is too many cats, which is, I don't know, but 10 is too few. And another way that we might concatenate strings together is to use this multiplication operator. So if we say S3 times S4, it looks like we're multiplying two strings together, but we're really getting this concatenation. Another thing to note is that in Julia we can't say S3 plus S4. That will not work. You could add a method, and we'll see later in the multiple dispatch section how you can add your own methods. So if you wanted to, you could add a method to enable this to work, but fundamentally the reason that it doesn't work is that addition is fundamentally a commutative operation, whereas multiplication is not. In the case of multiplying matrices, for example, the order in which you multiply matrices together matters. And when we're adding strings together or joining strings together, the order in which we want to join them together matters. Whereas the order that we add things together shouldn't matter. One of the examples at the end of this notebook that might be useful for you to try out is this one, asking us to concatenate the string hi 1,000 times. And so the idea here is that when we exponentiate things in Julia, really the star operator is getting called under the hood. And we just saw that the star operator allows us to concatenate things. So if I say hi to the 1,000th power, I'm going to get this super long string where I in a very friendly way, greet you 1,000 times. And that is it for the second notebook. Though I do encourage you, if you have a moment, to go through the exercises at the end of every notebook. I know that this tutorial is really fast, so we might not have time for you to do all of that here, but if you encounter any difficulties with any of the exercises at the end, feel free to, again, ping me or reach out on Slack or Discourse, and hopefully those exercises will get you, feeling more comfortable working with some of the basics in Julia, and also comfortable working in a Jupyter Notebook environment like this. For now, I'm going to close that, and let's go over to Notebook 3 on data structures, and I'll flip back to chat to see how we're doing with questions. Let's see. I have been confirmed as a crazy cat lady in the cat videos. Oh, and it looks like George Datsaris is on chat, and he is a very experienced Julia user, so hopefully he can help field some questions. And let's see. Yeah, I guess all the questions that have been asked so far have been answered, and so I will go back now to Notebook 3. So Notebook 3 is on data structures, and the three classes of data structures that we'll talk about in this tutorial are tuples, dictionaries, and arrays. If you're not familiar with the distinctions between those, from the user perspective, I think some of the most important differences for a user, I think, between these three different data structures, and I'll go over this again later, but they are that tuples are immutable. So once you've created a tuple, you can't update it. And otherwise, tuples are ordered collections of elements. Arrays, like tuples, are ordered collections of elements. So you can look up inside of an array and say, like, what's my fifth element? The same way that you can, inside of a tuple, say, what's my fifth element or what's my first element. But an array, unlike a tuple, is mutable. So we can update an array after we've created it. We can add things to it. We can remove them. We can change out some elements for other elements. And dictionaries are like tuples in the fact that, dictionaries are unlike both tuples and arrays in the sense that they are unordered. So we can't look up the first element of a dictionary. That doesn't really have meaning. And then dictionaries are like arrays in that they are mutable, so we can update them after we've created them. And with that, let's see what it looks like to make a tuple in Julia. So we can make a tuple by enclosing our elements inside a pair of parentheses. So my first example of making a tuple is here, where we're making a tuple called My Favorite Animals, which includes the elements penguins, cats, and sugar gliders. Now, once we've created this tuple, we can index into it because tuples are ordered. So we can say, I want the first element of this tuple, my favorite animals. And we do that by putting the number of the element that we're interested in inside square brackets after the name of the tuple that we're interested in looking inside. One of the things you'll notice here is that the first element is penguins, which indicates that Julia is a one-indexed language. So we start in Julia counting from 1, not counting from 0, the way that you might in C or in Python, for example. And now, as I said earlier, tuples are immutable. We can't update them. So if I try to change the first element of my favorite animals to otters from penguins, we see that there's no way to do that for a tuple. Now, as of Julia 1.0, named tuples are part of the base language. And what a named tuple allows us to do is to give tags or sort of internal variable names to the elements of our tuple so that we have a new way to perform a lookup inside a tuple. So that might look like this. Instead of declaring my favorite animals the way we did above, we might declare a new version of my favorite animals where the elements are still penguins, cats, and sugar gliders. The strings penguins, cats, and sugar gliders. But now we've assigned the variable bird to the first element, the variable mammal to the second element, and the variable marsupial to the third. So we declare this like so. And as before, we can use the number or the index of an element to look up what the value of that element is. So we can still say, what's the first element of my tuple? And we get that the answer is penguins, or the string penguins. But now we can also access, what is the bird variable inside my favorite animals? And when we do that, we see that, we can get penguins that way as well. If we were to switch this out, we could say, my favorite animals dot mammal, for example, and now we're grabbing the element associated with the mammal variable, or the name mammal inside of our named tuple. Okay, so next up is dictionaries. We can create dictionaries in Julia using this capital D-I-C-T, this dict function constructor. We could call dict without feeding it any input argument. So I could just create a D, for example, where I say D-I-C-T, parentheses, and now I've created an empty dictionary. Alternatively, we can initialize a dictionary to have key value pairs. Now the syntax for doing that is shown in a general way up here where my mouse is keying over. So we'll put the key and then an arrow that we create from an equal sign and a right pointing arrowhead, and then the value to the right of that. And then we use commas to separate our key value pairs. My first example of doing this is creating the dictionary called My Phone Book. So here we have the key Jenny associated with the value, which is Jenny's number, and then the key, which is the string Ghostbusters, associated with this phone number for Ghostbusters, included as a string. And having run this, My Phone Book exists, and we can perform a lookup, or we can see what the value associated with a given key is by throwing that key inside square brackets after the name of our dictionary. So if I say My Phone Book and then put the string Jenny inside square brackets, we get Jenny's number. And we can use very similar syntax to add additional entries or key value pairs to our existing dictionary. So if I put the value of a new key that I want to add to my dictionary inside square brackets after the name of My Phone Book, I can then put an equal sign after that and the value of the value that I want to associate with that key to the right of that. So here if we run this, we're adding Kramer and his phone number to My Phone Book. And if we run My Phone Book here, we can see that Kramer successfully added. So we now have 3 entries rather than 2. Another way that we might update a dictionary is to delete existing contact info or existing key value pairs. And we can do that by using this pop bang function. We'll talk in a later notebook, actually notebook 6, yes, in notebook 6 on functions, we'll talk about why some functions in Julia have an exclamation point in their names. But for now, we'll just say this is the function pop bang, which means pop followed by an exclamation point. Pop bang can be used to update dictionaries. And so if I call pop bang with dictionary as the dictionary name as my first input argument, and the key from the key value pair that I want to remove as the second input argument, and I run that, we're first off returning the value associated with the key value pair we're removing. And now if we look inside the dictionary itself, we see that Kramer has successfully been removed. Finally, I mentioned earlier that dictionaries are not ordered. That means that if I try to index into a dictionary with similar syntax to how I've indexed into a tuple, for example, I'm going to get an error. And the idea here is that because dictionaries aren't ordered, when you put a 1 inside square brackets after a dictionary name, Julia thinks you're looking for the value associated with the key 1. And there is no such key value pair that has 1 as a key inside the dictionary that we've created, so we just get a key error here. Now the final class of data structure that we'll talk about in this notebook is the array. And so we can create arrays in Julia by putting ordered collections of elements inside square brackets. And my first example of creating an array here is this one called My Friends. So one of the things that we see when we create an array is that we get a signature here that tells us first off how many elements are in the array we've created. So here we see there are 5 element array. And here we see what the type of the data structure we've created is. So this is telling us, if we read from the outside in, on the left we see the word array. This is an array that has dimensionality 1. So it's a 1D array. And what the value here says is what the type of the values included in this 1D array are. So this is telling us that this is an array of strings. Now, if we were to create another array called Fibonacci that has all integers, we see here that this is a 7-element array, and here we're saying this is again a 1D array that contains int 64s. Now there's no issue with creating arrays that have multiple types. So for example, here I'm creating this mixture array that has both integers and strings. And what we see here is that the type of the 1D array that's specified when we create this array mixture is the any type. Now we won't go into this in too much detail in this tutorial, but in Julia there is a type hierarchy, which I like to think of as I like to think of as a tree structure with the top of the tree being sort of where it all starts, the origin, rather than at the bottom. So in the way that I'm looking at my tree structure going down, at the very top is the any abstract type, and that encompasses all concrete types, all other maybe smaller abstract types in Julia. At the very bottom of the tree, we have the concrete types of Julia. So we have int64, float64, string, int32, float32, complex numbers. And sort of between that top of the tree and the bottom, we have some other abstract types like number, for example, which encompasses all integers, all floating point numbers, but isn't a concrete type, and it's not as general as any. That was a lot of information. If you're not familiar with type hierarchies, don't worry about it all. You don't really need to know that for the purpose of this tutorial. All you need to know is that it's fine to create data structures with mixed types in them, and that often those will be interpreted as in any type data structure. So with that, we've just created a few different arrays that were all 1D. If we want to index into a 1D array like this, we can do that by throwing the number of the element we're interested in inside square brackets after the name of the array. So here we grab the third element of My Friends, which is Barney. And if we want to update that element, we can do that by indexing into the array at the element that we want to change. And then to the right of that, we put the new value or the new element that we want to include at that position. So here we're changing Barney to Baby Bop. And I can prove to you that that happened by showing the values of My Friends here. So we see that Baby Bop got successfully inserted in place of Barney. Okay, so two other ways that we might update an array are to use the push bang and the pop bang functions. So first off, push bang will add a new element to the end of an existing array. And so the array that we want to update is our first element, and the elements that we want to, or sorry, it's the first input argument rather. And the element that we want to add to that array is the second input argument. So here I'm saying push bang Fibonacci 21, and I'm adding this number 21 to the end of Fibonacci. Now if we want to remove 21, for example, or whatever is at the end of an existing array, we can use this pop bang function. So if I say pop bang Fibonacci, we return the number 21, And if we look at Fibonacci now, we'll see that Fibonacci terminates with the number 13. If I were to rerun these cells, we would keep popping off whatever's at the end. So here if we run, we see 13, and now if I rerun Fibonacci, we see that the last number now is 8. So these were all examples of 1D arrays of scalars. But we can also have arrays that contain other data structures as their elements, and furthermore, we can have multidimensional arrays. For example, in Julia, a 1D array is referred to as a vector, so you can use either of those names and be correct. And a 2D array is referred to as a matrix. So a matrix is an example of a higher dimensional array. Let's start by looking at arrays of arrays. So here I've created this array of arrays called favorites. And one of the things that we see when we create this array is that we want to read from the outside in to understand what type we've created. So this is still a 1D array. We see this is a 1 for our dimensionality there. But now the element type inside of our 1D array is other 1D arrays that contain strings. And notice that this only has 2 elements because it only has 2 subarrays. Now here, I'm creating this array called numbers. And what we see when we look at this signature here is that we have a 3-element array called numbers, where this is again a 1D array that contains, as its elements, 1D arrays that contain integers. So it's like a container with containers, with things inside those smaller containers. Now, lastly, we can talk about multidimensional arrays. One function that happens to generate multidimensional arrays for us is this rand function. So if I run rand here, we'll see what it's doing. Rand, by default, is using the input arguments that I pass to it, the integer input arguments that I pass to it, to determine what the dimensions of the array it should create will be. And it will, by default, populate the elements, or as the elements of the array that it's creating with random numbers or pseudo-random numbers between 0 and 1. And so here, when I call rand on the integers 4 and 3, I'm generating a 4×3 random matrix. Now rand will take arbitrary numbers of input arguments. So if I call rand on 4, 3, and 2, we're getting a higher dimensional array, or in this case a 3-dimensional array, called, or not called anything, I haven't named it, but it is a 4×3×2 array now. And the last thing I want to say about arrays before we end this notebook is to be careful when you're trying to copy arrays. So we already talked about this array called Fibonacci. And let's say that I wanted to copy Fibonacci, and I think that I can do that by saying sum numbers equals Fibonacci. So if I do that, I have an array called sum numbers. If I index into sum numbers to try to change the first element to the number 404, we see that after doing that, if I look inside Fibonacci, Fibonacci has been updated. And the reason is that when I created the array sum numbers, I wasn't actually creating a new array, I was just giving a second name to an existing array. So if I want to avoid this, if I want to actually create a new place in memory, a new data type or data structure, when I'm trying to copy an existing data structure, I want to do that by using the copy function or the deep copy function if I want to do this recursively to generate something that has a container that has many containers inside of it, for example. So I'll show you, this is me using the copy function, but first we want to restore Fibonacci to its original state. So now Fibonacci starts with the number 1 again. If I copy Fibonacci to create this array called some more numbers, I can now index into some more numbers, change its first element to 404, and I can convince you I did that by running some more numbers there. So there we see 404 got changed. But if we look inside Fibonacci, Fibonacci starts with the number 1 still. So next we'll go to Notebook 4, and again we are still in the middle of our whirlwind tour of Julia's syntax, ending with Notebook 6, and then we'll start talking more about using packages in Julia. We'll do some benchmarking, talk a little bit about the design paradigm, and get to some linear algebra at the end. I will flip over to the chat briefly to see how things are going. Yep. So we got some questions about mutability and what the exclamation point means at the end of the functions that I use to edit dictionaries and arrays like push bang and pop bang. And I will talk about that more in Notebook 6, where we speak about functions. And so I won't address that on chat immediately. I think, yeah, addressing it verbally is probably fine. And then I'll come back to the concept of mutability in a later notebook. Okay, so where are we? All right, Notebook 4. All right, so this notebook is on loops, and we're going to cover in it the syntax for while and for loops in Julia. Now first off, to write a while loop in Julia, we use the while and the end keywords. And typically what we'll do is we'll put the condition that we are going to evaluate for veracity on the same line as our while keyword. And then we'll have, often for readability, an indented loop body between the lines that contain the while and the end keywords. So an example of what a while loop might look like in Julia is the while loop that I've included here, which counts from 1 to 10 and prints the numbers 1 to 10. And another thing that I'll note here is that this indentation, while nice for readability, is not necessary. So this loop will run exactly the same way if I simply indent the second line but not at all the first line. And I can add arbitrary numbers of spaces, because Julia for the most part is not white space sensitive. When I say for the most part, what I mean is that Julia can tell that there's a return statement here to delineate two different lines of execution. But Julia doesn't care about indentations or spaces. The second example of a while loop is here, where I'm iterating over an array to greet all of the inputs of that array. And now we'll do exactly those two same actions using for loops in Julia. So the syntax for a for loop in Julia is to use a for keyword, an end keyword to terminate the end of our for loop. And on the same line as this for keyword, we're going to put first a local variable that will take on the values of the elements in the collection or the range that here I'm calling my loop iterable, or the thing that my loop is iterating over. And we have this keyword in here to separate the variable that's going to take on different values and the loop iterable. And so here's an example of a for loop where we count from 1 to 10. And so we're assigning different values between the range 1 and 10 to this local variable n, and then printing the results. So this is the first time that we've seen a range in Julia. To create a range, we're specifying the beginning of our range, putting a colon, and then the end of our range. Another way that we might create a range is to specify how we want to step through a range, starting with our first number and ending with our last number. And we can do that by adding the step size as a third number between the beginning and the end, and then adding another colon to separate it from our other two numbers. So here I'm saying I want to take steps of 2, so I'm only printing the odd numbers when we run this loop. And similarly, as above, if we wanted to greet all the elements inside this array my friends, we could use a for loop to do that, where now the loop iterable that I'm using instead of a range is an array. And it could be any other type of collection as well. Okay, so in these next examples with for loops, we're going to create some addition tables. And really, so you know why we're doing this, the motivation is to show you different ways to embed for loops within other for loops. And also, we're going to slip in the notion of array comprehensions. But the way that we'll be doing this is by creating, as I said, addition tables, where addition tables are going to be matrices that for every element of the matrix, the elements will be equal to the sum of the row and the column index. And the first way that we'll do this is by initializing a matrix A to be filled with zeros, and we'll populate it thereafter with the values we actually want. Now we've generated this matrix of zeros here using the fill command. The fill command takes as a first input argument the value that I want to use to populate all the elements of the array I'm creating. And as the second input argument, I can pass a tuple specifying the dimensions of the array I want to create. So here I'm saying I want a 5 by 5 array that's filled with all zeros. Now that I've created that matrix A, we here are creating a nested for loop, one for loop inside the other, that goes over all the rows and all the columns of the matrix A and updates the elements to what we want them to be. Now, here's our first bit of syntactic sugar with generating nested for loops, that we can again start by creating a matrix of zeros, and now we can populate this new matrix of zeros B exactly the same way we did above, but with slightly different syntax. And we're doing that by removing our second for keyword and our second end keyword, and we are putting what was formerly our embedded for loop here, where we iterated over j from values 1 to n. We're putting that on the same line as the line where we tell I to go from 1 to m. And we've separated our specifications for what I should do and what j should do by a comma right here. And we can do this for arbitrary loop depth. We could, continue adding, k in 1 to, 10 if we wanted to, 1 to 10. But we won't. For now, we'll just create the same sort of addition table. And so that can give you, an edge. It's really nice if you have many loops to just be able to sort of specify everything at once. It can make your code a lot cleaner. And now the third way that we might have done this is with an array comprehension, but we haven't talked about array comprehensions yet. So I want to show you what that looks like first. Let's start by talking about a 1D array comprehension. So when I say array comprehension, what I mean is that I'm going to generate an array that sort of auto-fills itself. So I'm going to put code inside of an array to tell the array how it should be populated. So if I wanted an array from 1 to 10, I might just type the values that I want. I could say I want an array that has 1, 2, 3, 4, 5, etc. Alternatively, I could say, here are my square brackets. Inside my square brackets, I'll say for x in the range 1 to 10, include an x. And I'll say that by putting an x to the left of my for keyword. When I run this, I am going to get this array from 1 to 10. I can do more complicated or complex things here. I could say, for example, 2 times x for x in 1 to 10, and now we've doubled all the elements of the array there. So this is the syntax for an array comprehension. We can do this with multiple dimensions. So we could create an addition table, for example, with the code that I'm showing here, where again we have this syntax that we stole from above. If you were to scroll up, it would be exactly the same for that syntactic sugar embedded for loop. The first line of that for loop is this for statement that I have highlighted here. And then to the left of that, we're putting what was essentially the loop body of the previous for loops that we've written. And so here we've on the fly generated our addition table, and one of the things that's cool about that is this was the first time we created an addition table where we didn't have to pre-initialize that matrix of zeros. Okay, so that is it for loops. The next notebook is going to be, actually I won't close that just yet. The next notebook is notebook 5 on conditionals. And I will flip back to chat quickly to see if everything is okay. Let's see. Okay, so there's a discussion going on about references. Okay, great. And thank you, I'm sorry if I mispronounced names, but it looks like Camille has fielded, or yeah, Camille, perhaps Camille, I'm sorry, has fielded some questions about entering help mode, which is really helpful for some of our new users, so thank you. And okay, great, we see that someone likes the nested loop syntax. That's fantastic. All right, flip back to notebook 5. Okay, so this is notebook 5 on conditionals. And we start this notebook by talking about the basic syntax for a conditional statement in Julia, for which we use the if keyword, the else if keyword for additional conditions, the else keyword for our default option, and then our end statement, as with for and while loops, for example. Now the first example of using all these keywords that I will give is my implementation of the FizzBuzz test. Now, for those of you that might not be familiar, the FizzBuzz test is this commonly mentioned online interview question that novice programmers might get, where the idea is that I shouldn't say novice programmers, I should say programmers going in for a job to be interviewed. Anyways, the idea of the FizzBuzz test is that you're given a number or a set of numbers, And you want a test that produces the word fizz if the number is divisible by 3, that produces the word buzz if the number is divisible by 5, and fizz buzz if it's divisible by both 3 and 5. And so here, the number that we'll test will be 42, because that is my favorite number for obvious reasons. Yeah, maybe that's not obvious, but it's a Hitchhiker's Guide to the Galaxy reference, in case you're not familiar. Just being a little silly, but yes. So we will now test the number 42 with my FizzBuzz implementation. Okay, so what we're seeing here is that we get fizz because 42 is divisible by 3. So how did we check this? Other than using this if, else if, else end syntax, some of the new things that I'm showing here are this double ampersand. This also could have been a single ampersand, but that is something we'll discuss later in this notebook. Either way, ampersand or double ampersand is saying and. So that means we're checking that both of these two conditions are true. As for the conditions themselves, this one is checking for divisibility by 3, and we're doing that by checking what the remainder of n divided by 3 is with the modulo operator. And then double equality sign here is what's checking for equality between 0 and that remainder. Otherwise, I think those are the only new constructs that I'm showing here. So next up, I really like to talk about ternary operators in Julia because I hadn't seen them before coming to the Julia language, and so I think they're fun and very clean. The idea of a ternary operator is that we can rewrite a conditional statement written with traditional syntax like this that I have highlighted here. If A, then B, else C, end. We can rewrite that as a one-liner, or possibly a one-liner, depending on how much code you have, as such, without using the if, else, or end keywords. So let's see what that looks like in practice. So I'll start with two numbers, x and y, which are 3 and 4. And here we have a conditional statement that checks whether x or y is larger. So if x is larger, it's going to return x. If y is larger, it will return y. Really, if y is larger or equal to x, it'll return y. And so in any case, we're returning the larger of the two numbers. Now we could rewrite this exact conditional statement with a ternary operator right here. And so what I've done is I've taken the conditional statement that's being evaluated right after the if keyword. I've thrown that in, and really I don't even need this, these parentheses. And then we put a question mark after the conditional statement, so we're thinking, is that statement true? Question mark. If it is, do x, or return x, and if it's not, colon, then do or return y. And so we're getting 4 as above. So that is what a ternary operator looks like in Julia. And the last thing that we'll talk about in this notebook on conditional syntax is short circuit evaluation. So above, we showed that we could say and with a double ampersand like this. Now in Julia, we also could say and using a single ampersand. So for example, we could say, yeah, I don't really like that example. I'm gonna add some additional cells here. All right, so for example, I could say true and true, or I could say true and true. And those will generate the same result, as you can see there. Now what's different between these two different examples is that in the second example, what we're doing is we are short-circuiting our evaluation. So if, for example, let's say that this was the statement that I was evaluating. I'm saying false and true. So I want to see if both of those things are true. Again, we're returning the same result in both cases. But what's happening in this first case is that Julia is by default eagerly evaluating the statement. And so what that means is that Julia is going to see false, and then it's going to proceed and evaluate to see what the value of this second statement after the and sign is. In short-circuit evaluation, we terminate evaluation or we leave a statement as soon as we already have enough information to know the right answer. So in the case of false and true, as soon as we see our first false, we know that we could quit evaluation. And doing so would be more computationally efficient because then we're not spending time looking at whatever this second input argument to and is. And so with short-circuiting evaluation, we're not looking at this second input argument once we've seen that the first input argument is false. Now, a place where we can see that there's something slightly different going on here is when we have statements like this. So, for example, if we say false and true with this high statement thrown in here, we never actually see high get printed, and the reason is that this statement has not been evaluated. In this case, however, we do see that high gets printed here because Julia has seen a true, and so it proceeds to evaluate the second statement. Similarly, if you were to say true or print high, this, because we're short-circuiting, we're never actually going to get to the point where we say print high here. And in this example, if we say false or print high, we will actually evaluate the print high, though I think this needs an extra Boolean statement to, oh no, it works just fine. Okay, great. Yeah, so that's the idea, that we actually evaluate this statement here because this is false, and not here because this is true, and that's with short-circuiting. On the other hand, just to again show you the difference, if I remove one of these vertical lines to say or with only one vertical line, and I run that, we're now printing high, though it's getting angry here too. Technically, I need a Boolean statement here for it to be happy. So if I do that, now we print high and don't get any error messages. Okay, so that's it for Notebook 5. We have one more notebook in our whirlwind tour of syntax, and then we'll go over some other language features. So I'll open up Notebook 6 here. I'll flip over to chat to make sure everything looks okay. Let's see. Okay, it looks like we have some discussion going. Oh, okay, we did get one question about, oh, yep, and Sasha Mann is helping with that. Okay, yeah, we got a question about logical and between arrays from QX on the chat, and it looks like Sasha Mann is fielding that, but also that will come up in this last notebook on the whirlwind syntax tour that I've been promising when we talk about higher order functions. So that is coming up. So this last notebook 6 within our whirlwind syntax tour is on functions. So we'll talk about how to declare functions in Julia. We'll see a few different ways to do that. And then we will talk about duck typing in Julia, mutating versus non-mutating functions, which takes us back to that concept of mutability and why some functions end with an exclamation point. And at the end, we'll talk about higher order functions. And if you don't know what a higher order function is or what mutability is, that's fine. I'll show examples of both of those things to hopefully make them more clear. First off, how to declare a function. So Julia gives us a few different ways to declare functions. The first looks a lot like our syntax for while loops and for loops. We have now our function keyword and always an end statement. Now what we've done here is that we've put the name of the function that we want to declare and parentheses enclosing its input arguments after our function keyword, and then we have our function body on the line or in the lines between the function and the end keywords. So here we're declaring this function called sayHi that's going to greet whatever its input is via string interpolation. And here we have a function f that's going to square its input and return the square. Now one thing that you might notice here is that we haven't explicitly said what we want either function to return, what we want that return value to be. Now if we wanted to, we could say return x squared, for example. But we actually don't need to do that because in Julia, by default, whatever's on the very last line of a function will be what gets returned. So having declared sayHi and f in this way, if I call sayHi on the string C3PO, we get a greeting to C3PO. And here we square 42 to get 1764. Now next, another way that we could have declared either of these functions is to do so without using either the function or the end keywords. And we could do that by simply putting the name of the function and that name followed by parentheses enclosing whatever input arguments should go to the function, followed to the right by an equal sign, and then to the right of that, the function body. So this say hi to is going to do the same things that the first say hi function did, and this function called f2 is going to square its input just as the function f did. We can call functions declared in this way, just as we would call functions declared in the first manner. And the final way that we might declare a Julia function is to write them as anonymous functions, also known as the lambda functions. Now, why would we call something a lambda function? The reason that we use the term anonymous function, the reason we use the term anonymous function is because we can actually declare a function without giving the function any name. And we would do that with syntax like I'm showing in this highlighted line here. Having trouble highlighting, but yes. So in this highlighted line, what we see to the left is that we have some input argument, and if we wanted multiple input arguments, we could enclose them as a tuple. But we have an input argument separated from our function body on the right by an arrow that takes us from our input to our output. Now this arrow is created with just a dash and a right pointing arrowhead. So if I run this, I've now generated an anonymous function, and the function being truly anonymous here, I have no way to access the function thereafter. So I can't actually use it, which seems a little silly at first. If you're not familiar with anonymous functions or lambda functions, a very natural question is, why would I ever want a function that doesn't have a name? And I'll show you at the end that you can actually make use of functions that don't have names in particular contexts. But for now, if you like this syntax for generating a function, and you also want to give something a name, you can sort of cheat by assigning a variable to the anonymous function. So here if I say hi3 equals the function that I just declared, or f3 equals x to x squared, now I can access either of these functions by calling the variable say hi3 or the variable f3. And fortunately, the syntax that allows me to actually get at those underlying functions is the same as the syntax for calling the first two ways, or rather functions declared by either of the first two ways above. So now we've seen how to declare some Julia functions. This next section is on duck typing in Julia. If you're not familiar with the expression, if it quacks like a duck, it's a duck, that's where the term duck typing comes from, with the idea being that Julia functions tend to work on whatever inputs make sense. And I'll show you what I mean when I say that. So first off, we have this function called say hi that we've declared, and we've called it on a couple different strings, where those strings that get passed as inputs to say hi will get interpolated into an output string that's printed out. Now, we didn't specify at the time of declaring say hi that we wanted it to work on strings, but it worked on strings, and it will similarly just work on numbers. So under the hood, say hi is using string interpolation, and string interpolation will work with numbers just as well as with other strings. So here we're greeting a minor TV character from Peanuts, Schultz's Peanuts. Now similarly, we've seen that the function f works on integers to square them. But similarly, if we had a matrix A, for example, and we call the function f on A, we are going to get a valid output. And the reason is that matrix-matrix multiplication is a well-defined operation in Julia, and that's what gets called under the hood when we try to square a matrix. Similarly, we've seen that the star operator is defined for strings as a way to concatenate them. So if we call this squaring function f on the string hi, we get the output string hi hi. Now on the other hand, this doesn't mean that Julia functions will always work, because sometimes it doesn't make sense and they shouldn't work. An example of that is if we have a vector v, for example. Here this is creating a 3-element vector v, and if we try to call f on v, we're going to get an error. And the reason that we're getting an error here is that vector-vector multiplication is not a well-defined operation. When you try to multiply a vector by a vector, it's not clear if you're trying to take the inner product or the outer product of those vectors, or if you're trying to do element-wise multiplication. So next up is our section on mutating versus non-mutating functions. So when I say mutating functions, I mean functions that will alter the inputs that you've passed to them in the course of calling the function. On the other hand, non-mutating functions will take some input, they'll give you a distinct output, and in the course of running, they will not alter that input that you've given to them. And I'll show you an example of differences in behavior in a second to make that more clear. But for now, in Julia, we have a convention where functions that are mutating are terminated with an exclamation point. Now that is just a convention, so if you write your own function, it will still work with or without an exclamation point if it's mutating or non-mutating. But the convention is there to indicate to you as the user when you should be concerned or aware of the fact that calling a function might update the contents of some of the inputs that you've passed to that function. And you can trust that this convention is followed within the base language of Julia, for example, even though it's not enforced in your own code that you've written. So to look at the difference of a mutating and a non-mutating function, we can look at differences in behavior between the sort function and the sort bang function. So first here I'm creating this vector called v that has 3 input elements, 3, 5, and 2. And if we call sort on this vector v, it gets sorted to show increasing order, elements now 2, 3, and 5. But if we look at v after calling sort on v, v is still unsorted. It has not been changed by calling sort. On the other hand, if we call sort bang on v, we're going to get, again, the sorted version of the vector v. But if we look at the vector v itself, after calling sort bang, we again have the updated, or rather the sorted version of the vector v. So v itself has now been updated in the course of calling sort bang. And so that's what we mean when we say that sort bang is a mutable or a mutating function. Okay, so our last section in this notebook is on higher order functions. And a higher order function is just some function that will accept other functions as input arguments. Now a classic example of a higher order function, both in Julia and elsewhere, is the concept of a map function. And so what the map function does is that it takes some other function, and what it does with that function is that it applies it to all of the elements of some collection that the function map has access to. So an example of that is here. If we were to call map on the function f, and then the collection, or the vector that contains elements 1, 2, and 3, what map is going to do is it's going to apply the function f to each of the inputs of this collection, and it's going to return an array that has the result of applying that function to each of the elements of the input array inside of it. So here we're squaring the elements 1, 2, and 3 and getting the outputs 1, 4, and 9. I told you earlier that higher order functions, or at least that we're soon going to see a place where anonymous functions without names made sense. And that comes up here when we're talking about higher order functions. And the reason is that if we're passing a function to another function as an input argument, as we've done here, passing f to map, that function doesn't actually need to have a name to be useful to us now. So instead I could inside this, as an input argument to map, declare an anonymous function that I want to pass to map. So here I'm declaring this function that takes some input x, cubes the input to return this output x cubed inside my call to map. And there I'm doing element-wise cubing. Now, broadcast is another higher order function in Julia, and it's a lot like map, but it is more general, and so it works in some cases where map does not. For the purpose of this tutorial, we're going to treat broadcast like it's a clone of map, and for example, I'm calling it on f and this vector that contains 1, 2, and 3, and we're getting element-wise squaring. So if we're treating broadcast like a clone of map with a different name, what's interesting about broadcast still is that we have some special syntax for calling broadcast under the hood that allows us to use broadcast without explicitly saying broadcast. And we can do that by simply adding a dot after the name of any function that is in Julia or that we've written ourselves. And this dot is how we access broadcast now. So if I say f dot, parentheses, enclosing my input collection, f gets applied to all the elements of that collection. And to drill that point in home, let's say that we have a matrix A here that's going to have the numbers 1 to 9 from the upper left to the lower right-hand corner. Now if I call f on A to square it, we're getting A times A. On the other hand, if I call f dot A, Here we're getting each of the elements of this 3x3 matrix squared. And the reason that this dot syntax exists, there are a couple of reasons, but one of the reasons is that it gives you a way to sort of express the math that you might write down in paper in code in a way that's a little bit more natural or closer to the math that you might write down on paper. And so looking at this, complex expression with, multiple operations going on, it's sort of easier, I think, to look at this expression and have a sense right away of what operations are being performed on, which objects, versus, in this call to broadcast, we have, a lambda function declared inside the call to broadcast, and then A passes an input argument, and I believe this is cleaner. Another thing to note about broadcast is that both this dot syntax and the regular call to broadcast will perform exactly the same way. They'll generate similarly performing machine code, if not exactly the same machine code. And other than that, broadcast also does fusion of operations. So it doesn't create temporary variables when moving from the output of one pair of operations going on to another. It sort of does everything in place for you and thereby is more efficient. Okay, so that is it for our whirlwind tour of Julia's syntax. And now we're going to start to look at the package ecosystem, or at least how to pull in packages from the Julia package ecosystem. And I'm flipping back to chat quickly. Yeah, I'm getting some people saying that they wished that the compiler enforced the exclamation point convention for mutable. But otherwise, yeah, it doesn't look like there are open questions right now. Thank you so much to those of you that are helping field questions, Sasha Mann, for example. I really appreciate your coming out. And let's hop over. Okay, notebook 7 now. Okay, so at this point, Julia has over 2,000 registered packages. So packages are a huge part of the Julia ecosystem, and this ecosystem is still growing. And because Julia is a new language, and it's a new and growing language, one of the goals in designing the language from the beginning was to make sure that there would be first-class function interfaces to other languages. And so that's why there are packages out there like PyCall and rcall that will allow you to call functions from within the Python ecosystem or within the R ecosystem. We'll see in an upcoming notebook that you can actually declare C code or use C libraries within our Julia environment. Similarly, there are other packages that have been implemented in other languages or other libraries from other languages that have been wrapped in Julia, so that you can access that functionality from within Julia. And the idea is that having great foreign function interfaces will allow users who are interested in trying out Julia but don't want to switch over their entire workflow all at once easier to start making that transition and to see what it's like to play around in Julia. So you don't have to wait until the ecosystem's fully mature. You don't have to make a hop all at once. You can keep using your favorite language, your favorite library or tools from another language as you're starting to learn Julia. Now, to see what packages are out there, you can go to either of the links that I provided here, either pkg.julialang.org or juliaobserver.com. And that's where you can see what the Julia ecosystem looks like. And the purpose of this notebook is really to show you how to start using a Julia package, how to use the Julia package manager. So first off, we won't have to install packages in this environment today because packages have been pre-installed for us, but I've included code to show you what installing a package would look like. So whether you're in a Jupyter Notebook or at a Julia REPL, the first thing you'll want to do is say using PKG if you want to install a package. After saying using PKG, you would then install a package by saying pkg.add, and then inside parentheses after the call to add, you would put in quotation marks the name of the package that you want to install. And you only have to do that installation once for a given Julia binary, and then you never have to do it again. But every time that you use a package in a given Jupyter Notebook or script or REPL session, you always need to load that package with the using keyword. So here I'm saying using example to load the example package. And now that I've done that, I have access to all of the source code in the very verbose example package at this GitHub link. And what you would see if you went there is a function declaration for this function called hello, which calls a string and greets it. And now that we've loaded the example package, we have access to that source code. So we have access to this hello function, and we can use it to print some lyrics. Another fun package to demo is the colors package. This is how we would install the colors package. We don't have to do that on JuliaVox because it's pre-installed for us. So we can say using colors to load the colors package, which gives us access to this function from colors called distinguishable colors, which generates a color palette for us of however many colors that we specify here. So this is generating a palette of 100 different colors. And one of the things that I like to do with this color palette is use it in calls to the rand function. So we've already seen that this rand function will generate arrays for us. So for example, if I say rand on 3, 3, I'm going to get a 3 by 3 matrix of random floating point numbers between 0 and 1. What I haven't shown you yet is that if you want to randomly populate your matrix with something other than floating point numbers between 0 and 1, you can optionally pass as the first input to rand a collection. And that collection could, for example, be a range, like the range 1 to 10. And now I'm going to populate my 3 by 3 matrix with integers between 1 and 10. Now, on the other hand, this is actually really amazing. We don't have any duplicates there. That's great. Anyways, another collection that we might pass to the rand function is the color palette that we've just generated. And this is a fun example because every time you run it, you get a differently checkered or colored matrix. Okay, so that's how we use packages in the Julia ecosystem. And we will make use of them in this next notebook on plotting. So there are lots of different ways to plot in Julia, but in this notebook, 8, I'm going to show you how to plot using plots.jl. One of the things that's cool about the package called plots.jl is that it gives you a common set of syntax to use multiple different backends. So you can write code to generate a given plot. You can generate that plot, and then if you want to switch out the backend and switch from using, for example, pyplot to plotly.js or gr, you can do that without needing to rewrite any of the code that you use to generate that plot, other than one call to a new backend. So I'll show you that in this notebook. We start by saying using plots I've actually already run this notebook, but we start by using plots here to load the plots package. And then the data that we'll be using to demo plotting is this global temperatures and number of pirates data. So this gives us some data that I've thieved from the internet, where for a few years between 1860 and 2000, we have global temperatures in degrees Celsius and pirate populations in number of pirates. And what we have here from left to right in the ways that I've populated these arrays are data for years going forward in time from left to right. So here I load the gr backend, so that's the first backend that we're going to demo. And then here I'm using the plot command and the scatter bang command to plot global temperatures against the number of pirates. So what we've done here is we've used the plot and the scatter bang commands to generate an overlay of points and a line plot. One of the things that I'll have you note here is that we've used scatter bang instead of scatter. If we had used simply a call to scatter, we would have generated a scatter plot. But if we want an overlay of multiple pieces of data or multiple views of data, we would generate that overlay by mutating the plot that we created in this first call. And there are a couple different ways we could do this. Here, when I've called scatter bang, Julia has just assumed that the plot that I'm updating is the plot that I generated last. If I'm generating multiple plots and I want to be precise about which plot I'm going to use for an update, what I could do is I could name a figure like my fig, for example, and then I could say scatter bang, and I could specify that my fig as the first input is the plot that I want to update, and that would work just as well. But here I don't need to do that because I'm only working with the plot that I just created. Now we can mutate this plot a bit farther to add some extra information about what the plot is showing and what our axes mean. And so I've labeled the axes with these x label bang and y label bang commands, which tell us that on the horizontal axis we have numbers of pirates and that it's an approximate figure, and that global temperatures are given here on the vertical axis. And the title bang command here has given us this
lovely title, which shows us that this data is telling us something about the influence of pirate populations on global warming. One thing that looks a little odd here is that it looks like pirate populations are going down from left to right, and similarly global temperatures are going down. And the reason that this is a little odd is that by default, Julia is plotting whatever's on our horizontal axis in increasing fashion. Oh, sorry, I think I said that wrong earlier, that this looks like the number of pirates is going up. Yes, because Julia is plotting in increasing fashion from left to right. But actually, pirate populations have decreased since the 1860s, and so if we want to see that pirate populations have decreased and be thinking about our data from left to right, we would need to flip this plot, and then we'll see, going forward in time from left to right, what has happened to global temperatures. So we can do that flip with this xflipbang command. Okay, and so this is what we see here. Now we have data from 1860 to 2000 going left to right, and pirate populations are decreasing, as you might better expect, as global temperatures are rising. I have been told to say that this is a correlation causation joke. That may not have come across to all of my audiences, and yes, just to be clear, this is a joke. Yes, so we don't really need more pirates, hopefully, to prevent global warming. Okay, so what might we do next? What we might do next is show that we can generate very similar plots now with different backends without changing our code. So this is the code that we use to generate the plot above. Here what I've done is I've called the pyplot backend, and now we're getting a pyplot version of this same plot. Another thing that another backend we might use is this one called Unicode plots, which doesn't work perfectly in this particular context because it doesn't seem to have the xflipbang command, but just to give you a sense of what a very different backend might look like. Oh, and that it needs to be smaller for you to see what's going on here. There we go. Okay, so if I make this plot much smaller, then you can actually start to see it. There we go. Okay, so that's Unicode plots. And the final thing I like to show in this notebook, oh, I have a bit of a lag on, I think I'm running too many things on my machine at once. So there we go. Zoom back in. Okay, hopefully you can see my stuff again. All right. Scrolling past our Unicode plot, the last thing I like to show here is how to create subplots in a larger plot. And we've done that in this last exercise here. So first off, here I'm declaring this range x from -10 to 10. And what has been done in this exercise is that I've generated 4 different plots and bound each of those plots to variables p1, p2, p3, and p4. And finally, I've called plot a 5th time and then fed these plots p1, p2, p3, p4 as inputs to this 5th call to plot. And I've specified how I want the layout to look of these individual plots, which are going to be subplots within my larger plot. So here when we say layout 2, 2, we get this 2x2 grid of plots. We similarly could have said, 4x1 or 1x4 to get a different layout. So that's it for our plotting story. And let's go now to notebook 9. It's at the bottom. I don't want you to see the end before we get there. But okay, so this is notebook 9. It's called Julia is Fast. And the purpose of this notebook is to do some benchmarking. To get good statistics, sometimes running benchmarks isn't an instantaneous sort of thing, and so I pre-ran this one, and then we'll scroll through and uncover the results as we go. So the purpose of this notebook, or rather one of the things we're going to do in this notebook, is look at different implementations of the sum function. So this sum function is going to take a vector, and it's going to add together all the many elements of that vector. Now we're going to look at implementations of this sum function from C, Python, and Julia.
Now, in particular, we're going to look at two different versions from C, which are both handwritten. The first will have no optimizations, and the second will be compiled with the fast math flag. Then for Python, we're going to look at the built-in version of the sum function, the NumPy built-in version of the sum function, and then also a handwritten implementation. It uses the same algorithm as the handwritten one in C, again without optimization. And then finally, we'll look at three different versions in Julia. We're going to look at a built-in version in Julia, a handwritten in Julia, and then a handwritten that we've optimized a little bit using single instruction, multiple data. And so we'll get started with that now. So we can first generate a vector A with 10 million elements that we're going to use for all of our benchmarking purposes. So we're creating A with this rand command here. And as a sanity check, we're calling the built-in version of sum from Julia on A to see that sum is giving us what we might expect our output to be. And so here when we call sum on A, which is 10 million elements, we basically get 10 million times whatever the average number in the vector A is, which should be about 0.5. And so we would expect to get an output of about 5 million, and that's what we get. So this is giving us sane behavior. Now to do benchmarking, we're going to use a package called benchmark tools. We do have the option for timing things in Julia to use this @time macro, which will tell us how long the code following that macro took to run. The thing with the @time macro is that because there are other things going on my machine, for example, and just variability from one run to another, we're going to see higher variance in how long one run takes versus another. And we see that here. When we call sum on vector A 3 different times, we get 3 very different numbers. So benchmark tools has been created to give us a better way to benchmark that provides some statistics on every piece of code. So it'll run that piece of code many times, and it's a variable number of times depending on how long it takes for the average time to converge. So it runs a piece of code many times, gives us many samples, and then it provides some statistics on what the average runtime was, the best runtime, the worst runtime, so we can have a better sense of what the performance of that code looks like on average, and in the best case and worst case scenario. So here we're using benchmark tools, and we're going to start by looking at our implementations in C. First, just the regular unoptimized handwritten version in C. And I didn't write this notebook myself, I should say, so you're welcome, like me, to treat much of the C code here and the compilation flags as black magic. Even if you're treating this as black magic, one of the things that's cool here is that we are declaring and compiling C code from within a Jupyter notebook. So this is our C code. This is our implementation of sum, and we're compiling that here. And once we've compiled it, we're using this C call function to call out to some precompiled C function or C library basically, and we are assigning it to this function called csum, which is going to work on arrays within our current scope. And so we call csum on our vector A here, and as just a sanity check, and we see that we get about 5 million. As another and better sanity check, we see here how the output of csum called on A relates to the built-in version of sum from Julia's output on A. And we're doing that using this isAprox function, for which the documentation is shown here. If you do !isAprox, you can see that isAprox will compare two numbers and check to see that they're the same within some tolerance that you can specify yourself if you're interested. And then these curly braces here are a way of calling the isAprox function. Here, one of the things that's being shown is just what the actual difference between csum's output and sum's output is. And a final thing before, or I guess here, first we benchmark. So we're using this @benchmark command from the benchmark tools package. We're calling that on the function csum, and we see that our best case runtime is under 12 milliseconds here. So what we're going to do is we're going to take that best case scenario extracted from our output from benchmarking, and we're going to add this best case scenario after normalizing to get rid of milliseconds. We're going to add that best case scenario to this output dictionary D, which is going to store all of our results so that at the very end we can compare in a clean way how all the different implementations worked.
And the last thing that we're showing here, just to give you a little bit more of a sense of how benchmark tools is working, is a histogram on all the different run times from various samples on calling csum, how long these different runs took. And so we can see that there's quite a bit of variance in how many milliseconds this took, from roughly 11 to maybe 19 milliseconds. And we can see that the average runtime is about in here, and it's again this best case scenario from down here that we're actually going to be using for a strict comparison between the different implementations and different languages. Okay, so now that we've looked at the handwritten version of C with no optimization, we'll add a bit of optimization by compiling the same code that we did above, but we've now added this fastmath flag. And now we're getting this function called csum fastmath in Julia. And when we benchmark that, we see that now we've cut our runtime by more than a factor of 2. So we're down to just under 5 milliseconds now for this somewhat optimized version in C. So we're adding that to our output dictionary, and then we will move on to our implementations in Python, starting with Python's built-in version of sum. Now we're going to grab built-in functions from Python using the pycall package here. And pycall gives us this function called pybuiltin, to which we pass the name of the function that we want to grab. So we're grabbing sum from within Python, calling it pysum in our current scope. Here we're doing a couple sanity checks to make sure that pysum is operating the same way as our other sum functions. And then we benchmark pysum. And when we benchmark pysum here, we're seeing that the built-in version of Python sum is taking about a second. Okay, so we add that to our dictionary D, and then we can move on to NumPy. To grab functions from NumPy, we're going to use this conda package, and then this pyimport command to specify which function we want from NumPy. We do our sanity checks a little bit later down here, but before that here we're benchmarking. And when we benchmark this, we see that it takes about 5 milliseconds for NumPy's version of sum to work. So it's much faster than the built-in version in Python because NumPy has more information about types and how to work with arrays. So we add that to our output dictionary D, and we see that Python's NumPy is performing comparably to C fastmath at this point, which makes sense because NumPy should have optimized C code running under the hood. And I should say that even with benchmark tools producing statistics that give us more precision than say the @time macro would, we are still going to see some variation from one benchmark with benchmark tools and another. And so for example, the amount of variation that we see between Python's NumPy here and C with fastmath, I wouldn't say is a very meaningful difference. Or perhaps I wouldn't feel confident saying that it was meaningful at all, to the contrary. So lastly, for Python, we will look at a handwritten implementation of Python, Python sum. And so to do that, we're enclosing our Python code inside a string here, and then we're using this py keyword to indicate that this is some Python code coming up. We use that py keyword here as well. And then we're calling this Python function sumpy in our current scope. And we benchmark it here and see that our handwritten implementation is taking about 1.2 seconds here. So that's our slowest one so far, as we would expect. Yeah, given that we haven't optimized it and it's a relatively simple algorithm. So we add our Python handwritten to our output dictionary D here. And then we can move to our implementations in Julia. So we'll start by looking at our built-in version of sum from Julia. Now that built-in version is just named sum, and what this @which command will do here is tell us where we can find sum, or which version of sum is getting used. So it's telling us that sum is written or declared inside the file here in the base language. And if you were to go to this file, what you would see is that sum is actually written in Julia itself, so it's not implemented in like a lower level language. Yeah, a lower level language like C or Fortran. So when we perform our benchmark on our built-in Julia, we see that that is taking about 4.8 milliseconds. We add that to our output dictionary, and we see that that's performing comparably to C with the fastmath flag here, and also comparably to Python's NumPy, which has, again, optimized C code under the hood. So we can move now to our Julia handwritten, which looks pretty similar to the Python code that we wrote above. And when we benchmark our handwritten version of this sum function in Julia, we see that it's taking just under 12 milliseconds, which is comparable to this handwritten version in C, which also wasn't optimized. And finally, we can move to our handwritten version of Julia using SIMD. So we use single instruction multiple data by just adding this @SIMD command in front of our for loop here. And adding that small additional syntax to perform this optimization, when we run a benchmark on this, we see that we've taken our handwritten Julia down to the performance of our optimized or our built-in version of sum within Julia. And so we add that to our output dictionary, and then we can order our results and see how everything did. And really the takeaway here is that, first off, there are multiple takeaways. One of the takeaways is that our optimized Julia code is performing comparably to our optimized C code. Similarly, our unoptimized Julia code is performing comparably to our unoptimized C code. Beyond that, another thing that's cool is that, just working with our Julia handwritten code, or, writing something in Julia ourselves, which is something we will necessarily have to do once we start working with more complicated operations and want to write things that are custom. Doing that, we're getting speed and performance that is roughly, it's here a little bit more than a factor of 2 slower than here. I meant to show the built-in one. But that factor of 2 really isn't like that big of a difference. It's amounting to performance of a few milliseconds, whereas if we were to look at, for example, the difference in performance between like Python's NumPy, where we very well might go to get speed out of Python versus something that we might write custom in Python, the difference there between what has been optimized via more time and investment and what we've just sort of written on the fly is much larger. So that is our Julia is Fast notebook. And next up, we have a notebook on multiple dispatch. So the point of this notebook on multiple dispatch was going to be to start to give you a sense of why Julia is fast. And once we've gone through this, I'll try to run through some linear algebra quickly, since we still have only about 7 minutes left, but I might run over by maybe 5 minutes or so. So here, notebook 10 is on multiple dispatch, and it is the design paradigm of Julia. So it's what makes Julia so generic and so fast. So to talk about multiple dispatch, we're going to start by talking about some things that we've already seen. So we've already seen that we can declare a function f, for example, and that we don't need to specify what f takes when it squares things. Julia figures out on its own that f is perfectly capable of squaring integers and matrices and strings to concatenate them together, but it also figures out on its own that that f does not work on vectors because there isn't a well-defined way to multiply vectors by one another in Julia, or more generally in math. And so Julia figures this out for us. Now, if we wanted to, we do have the option in Julia to specify the types of our input arguments. And so that's what I'm doing in this example here when I declare a function called foo. This is not it's not at all a meaningful name. It's just some random function. The point is that I'm declaring some function that does something, and it takes particular types. In this example, foo is taking 2 strings, and it's going to print, when it gets called, that my inputs x and y are both strings. Now, we know that it's taking 2 strings because of the annotation here. So if I want a given input argument to be of a certain type, I'll follow the name of that input argument in the function declaration by 2 colons here, and then the name of the concrete or the abstract type that I want that input to be. So here I'm saying x : string for x is a string, and also y is a string. When I declare this, foo now exists, and I can call this function foo on 2 strings, for example, hello and hi, and that works the way that we might expect it to. Now, if I call foo on 3 and 4, it doesn't work, and the reason it doesn't work is that I didn't write foo in a way where it should work.
there's no way to call foo on two integers because foo only accepts strings the way that I defined it. Now, if I want foo to start working on integers, I can write foo such that it does. And I can do that by saying, okay, well, now I want x to be an integer and I want y to be an integer. This is my new foo, and when this foo gets called, I want you to print that both x and y are integers, as they are constrained to be. So now when I call foo on 3 and 4, I'm getting this now expected output, my x and y are both integers. So we know that this foo is being called when I call foo on 3 and 4. So where this starts to get interesting, and where we start to get a hint of what multiple dispatch is and what it's doing, is that when I call foo on hello and hi, these two strings, I'm still getting this output that x and y are both strings. And the reason is that when I wrote foo here, when I wrote this definition for foo that takes two inputs, x and y, I didn't replace my original definition for foo up here. I didn't overwrite this definition. What I did was I added a second definition, and in Julia that's perfectly fine. I can write many, many, many different definitions or implementations with, for one function name. And so the idea, behind a multiple dispatch is that, or one of the key concepts there is that we have a distinction between generic functions and methods. So generic functions are sort of, we can think of those as sort of the abstract ideas that we have tied to particular operations. So what I mean by that is that, we in our minds might have an idea of what it means to add things together or what it means to subtract things. And, when I, as a human, am thinking about adding two things together, I'm not thinking about, using different algorithms for adding together floating points versus integers. I do those, in very similar ways. But on a computer, we need specific implementations for adding together, strings or adding together int64s or int32s because of the way that those numbers or generally those values are stored or represented on a computer. And so, we as the users might want to just think about these sort of general ideas like addition and multiplication, whereas a computer needs, again, these specific implementations for specific types. Now, generic functions are sort of these general, more loosely defined ideas associated with operations, and methods are these specific implementations for particular types. I thought I had something to add there, but I'll come back to it if I remember. So the idea is that we as the user in Julia can work with these more generic function types. We can just use functions like foo, or we can add things together, and we don't have to specify, what types we're going to be adding together in advance of calling addition. Julia is going to figure that out for us by relying on, built-in functionality that has specific implementations for all of these lower level operations that have already been, well optimized for particular data types. So one way that we can see how many different methods exist for a given function is by using this methods function. So if I call methods on the function foo, we can see that there are two different methods for foo sitting around. One is for foo that works on two integers, and one is for foo that works on two strings. Similarly, if I were to call methods on the plus operator, we see that in Julia there are 163 different ways to add things together. So this is basically a combinatorics problem where we have, adding big floats to big floats, and how do we add dates to other dates, and complex numbers to complex numbers, reals to complex, and what have you. So another really useful function when we're starting to think about multiple dispatch is, how do we actually tell what version of a given function is being dispatched? And for that we can use this @which macro. So this @which macro we saw before in Notebook 9, what it's going to do is it's going to tell us which version of this foo function, which method associated with the function foo is actually being sent out when I call foo on these particular input arguments. So when I call foo with 3 and 4, we see that the version that's being dispatched is int64. We don't need to have a particular return type to see which version got used. Similarly, if I call @which on 3.0 and 3.0 here, we see that the version of addition that's being called under the hood is the version that
works for float 64s. So I guess one of the key ideas here is that there's this traditional understanding that there is a necessary trade-off between the speed of lower level languages and the ease of use of higher level languages. But what's going on here is that we've really gotten the best of both worlds, and the way that we were able to do that is that we've taken advantage of the fact that the way that lower level languages, or languages that generate more efficient machine code, get so fast is that they're able to make use of additional information. If we're coding in C or if we're coding in Fortran, we tell the compiler up front, like, this is an integer, or like, this is a float, and then the compiler can use that information to apply constraints that allow it to perform optimizations that that we luckily don't have to do. When we're working in a language like Python or MATLAB, we aren't able to communicate with the compiler in that way, or the interpreter. We're not able to say, this is an integer, therefore do things really fast for integers. But in Julia, we've sort of abstracted away that part where we provide that additional information to the compiler, so the compiler can take advantage of type information because of this design paradigm, multiple dispatch. It has the advantage of taking that information into account, but we as the user don't have to specify it, because we can just work with these generic functions that allow us to work with these more abstract ideas and not worry about those lower level implementation details. So with that, I did mention earlier very briefly this notion of a type hierarchy in Julia, where I said that at the very top of our tree we have this notion of an abstract, an any type that encompasses all concrete types, and then these concrete types at the bottom with other abstract types in between, in the middle layers, like number, for example. So this number abstract type includes all integers and floating point numbers. So in this next example, when I say that x and y are both going to be number inputs, and then I'm going to print accordingly that x and y are both numbers, I now have created a way for foo to work on any number for which a method hasn't previously been specified. So if I call foo on 3.0 and 4.0, I'm getting this method declared for numbers being called. If I went back to foo being called on just 3 and 4, we're still going to go to the most specific implementation, the version that was already written for integers, rather than using the general number version. And finally, we can always declare functions in a way where we've provided a fallback or a more generic use case. So for example, here I'm declaring foo without specifying what x and y are, and now when I call foo on a vector, I'm going to get an output that calls this function. So that's our very much whirlwind tour of multiple dispatch, and in the next few minutes I'm going to go quickly through some of the linear algebra content, starting with notebook 11 here, where we'll talk about basic linear algebra syntax. So in this notebook, I'm starting by creating a matrix A with the rand function that we saw in some earlier notebooks, and then I'm going to create a vector x with this fill command. And I'm using, I'm using these functions ren and fill to create x and a, so that we can generate a linear system. So first off, we can do matrix vector multiplication with the star operator. So here we're saying a times x equals some vector b that's being returned there. If we want to transpose a matrix, we can get conjugate transposition by using a little, I'm forgetting the name, but apostrophe. A apostrophe gives us the conjugate transpose of A. And if we want simply the transpose, which in this particular case, because I'm working with reals, is the same, I can use the transpose function. In Julia, we can do transpose multiplication without specifying that we're multiplying. So if I say A prime A, Julia understands that I want A prime times A. I don't explicitly need that multiplication operator there. And then to solve linear systems in Julia, we can use this backslash operator. So if I say A backslash B, I'm going to solve for x, and this will work independent of, oh no, this is what happens when you generate random matrices and then rely on them. So if I generate a new matrix, chances are this will not happen again. There's my new linear system. If I try to solve now, okay, this time I did not generate a singular matrix randomly. I generated something else. So here we're able to use the backslash to solve ax equals b for x. And we can use the backslash to solve linear systems even when we're working with non-square linear systems. So for example, if we now generate this matrix called A tall, which has more rows than columns, I can solve A tall backslash B for my solution via least squares solution with the same backslash operator. Similarly, let's say that I was working with a rank deficient linear system. What I mean by that is that here I've created a vector v, and then I've created a matrix that has as each of the columns that same vector v. So this system is rank deficient, and if I solve with the backslash operator here, now I'm just getting whatever the minimum norm least squares solution is. And similarly, we'll get the minimum norm least squares solution if we're working with a short matrix A, or one that has more columns than rows. And again, just use the backslash there to solve. One of the things that's mentioned here is that there's now the linear algebra functionality within Julia is now stored within this standard library called linear algebra, which we will need to import or load for some more complicated linear algebraic expressions, as we'll see in the next notebook. So the final notebook to our tutorial is this notebook 12, which shows some more fun linear algebra things. So notebook 12, factorizations and other fun, we're going to talk about factorizations. I'll show you some utility for working with special matrix structures, and then we'll talk a little bit about generic linear algebra. So first off, we're now bringing in that standard library linear algebra, or the package now linear algebra, using linear algebra, and we're generating a linear system here. So we have A, X, and B by the time this has run. So we're starting off by talking about factorizations, which are, we can think of factorizations, if you're less familiar, as a way to express a matrix as the product of other matrices, or perhaps as a way to sort of break up the way that we express a matrix into other matrices. So we'll start by talking about an LU factorization, where the formula for an LU factorization is shown here. And the idea is that we start with a matrix A, we want some other way to express A, and so we express A as the product of the matrices L, a lower triangular, and U, an upper triangular matrix, and then also this permutation matrix P. So we can perform an LU factorization in Julia by saying LU and calling that on the matrix A. And here we're going to get a factorization object out that contains the matrices L and U, and those are getting stored in this particular piece of code in this object called ALU. When I look at the type of ALU, we can see that it is this LU type, and now I can look inside ALU, or inside that LU type, by saying .p, for example, to grab the permutation matrix, ALU.L to grab the lower triangular matrix, and ALU.U to grab the upper triangular matrix. There are methods that we can dispatch on, or rather, sorry, there are methods that allow us to dispatch on different types. So we can, for example, solve our linear system by calling the backslash operator here, saying A backslash B, as we saw before, or if we call the backslash operator here, we are dispatching on the type of ALU, which is a factorization object, to use the factorization we've already done to solve the same linear system. Similarly, just as we could grab a determinant in Julia by saying det on a matrix, we could call det on a matrix factorization object and get the same output. Now, the syntax for working with a QR factorization, and generally other factorizations in Julia, will look similar to the syntax that we just saw above. Here, the function call for performing a QR factorization is QR, and again we're going to get a factorization object out, which will contain the matrices that we're interested in, the matrix Q and the upper triangular matrix R. And we can reach inside AQR, which is our factorization object, to grab the matrix Q by saying AQR.Q, and we can grab the matrix R like so. Similarly, eigen decompositions can be performed with this eigen factorization function. So when we call eigen on this symmetric matrix asim here, we're getting this factorization object asim I,
and we can reach inside that and grab the eigenvalues or the eigenvectors like this. So basically, whenever you're working with a new factorization and you want to know what keywords you need to grab the particular matrices that have been factorized or produced as a result of your factorization, you would just want to look at the documentation for that particular factorization function. All right, another thing to note here is that when we take the inverse of this factorization object, asymeig, what we're actually doing under the hood is that we're making use of the eigenvectors and the eigenvalues to generate the inverse, as is shown with the formula here. And I am actually going to have to cut out now, unfortunately. I guess I won't get to cover special matrix structures till the next tutorial, but unfortunately this room is taken, so I have to cut out. So thank you so much for watching. I am going to turn off my video, but I will flip back to our intro slides here so that you have a list of resources. Nope, that's not what we want. There we go, resources. So thank you so much for watching and have a great day. Bye.